Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. As science uncovers more about materials, it can become harder to do something brand new. One avenue is to transfer concepts from one area of science to another, with some surprising results.
We've been talking a lot about how to transfer concepts from semiconductor devices to electrochemical systems. The thought is to just take tricks that people do with semiconductors, but instead of conducting electrons, we're going to do the same stuff for ions.
That was Professor Gideon Segev from Tel Aviv University in Israel and Lawrence Berkeley National Lab. The concept that Gideon's team developed looked a lot like a ratchet, a non-equilibrium device that utilizes temporally modulated input signals and spatial asymmetries to drive a steady-state particle flux. To drive a flux of charged particles, a structure resembling a capacitor was developed. The capacitive ratchet mechanism has advantages over utilizing redox reactions, including a lower voltage. Where redox reactions need at least 1.23 volts, the ratchet can work using voltages as low as 50 millivolts. Importantly, the ratchet is also selective. Ions can be sorted based on their diffusion coefficient by selecting the appropriate frequency for the input signal. This opens doors for efficient devices for desalination and selective ion separation. As Professor Shane Ardo from the University of California puts it,
if the goal is to move ions from one side of the device to another, you wouldn't draw a chemical reaction necessarily that involved doing a redox reaction. So it's advantageous if you can find a mechanism by which you didn't have to use the redox reaction because that's not necessary for the things you're looking to do.
The most recent work demonstrates the ratchet-based ion pump experimentally using off-the-shelf nanoporous anodized aluminium oxide wafers, which had the planar surface of the wafers coated with a thin layer of metal.
Essentially, the device is a membrane that has two metal layers, thin films on the two sides. And so we put it as a membrane between two compartments of electrolyte and basically apply different signals between the two surfaces. So basically applying different square waves across. And what it does is that the square wave induces what we call capacitive ratchet mechanism that drive ions from one compartment to another. In the paper, one of the things that we did is to use this driving mechanism inside an electrodialysis-like setup, in which you have also an anion exchange membrane, which transports only anions, and cation exchange membrane, which transports only cations. And we use this asymmetry in order to actually desalinate water.
The device is based on a previously published theory. Further modelling work to describe the device led to new insight and uncovered some counterintuitive behaviour.
You were modeling things and simulating, and something came out of it that was unexpected, that presented itself as almost a different architecture than one would typically design an electrochemical device. In electrochemistry, you need two pathways for the current to flow. You need one pathway, the electrons flow in the external circuit, and then the ions are flowing to match that current. So you have a net cyclical pathway for the current. What Gideon's model had shown was that you didn't need necessarily a second pathway. You could have two different ions moving through the same pathway, and that would be able to constitute this kind of net two pathways of current. It's called an ambipolar transport. And the ambipolar transport could mean the ratchet could be pumping, for example, a sodium one direction. And because of the oscillatory nature of the input voltage, you could kind of walk the chloride with it.
The modelling suggests instead of using two membranes to transport different ions, only one membrane may be required, which simplifies the electrodialysis setup. Although this proof of concept has used an off-the-shelf component to demonstrate the ratchet mechanism, future work will focus on designing a new material system from the bottom up, based on the modelling work. Like many breakthroughs, demonstrating this ratchet mechanism is the result of collaboration between people with different expertise who bring different schools of thought to tackle a challenge. This work was published in a recent issue of Nature Materials. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.